Okay, what about Bell's theorem? Why doesn't that work? Well, let's start off with two entangled particles. One gets shunted out that way, the other one goes that way. And this is a particle detector. This circle is the interface between quantum and classical reality, and you can measure any directions at all, but let's say they're measured like this according to Bell's theorem, and then here they're measured like this, and then you just measure every possibility, and then you share your data later. So let's see the possibilities. So 1, here's a possibility, the measurement goes that way, and let's say 1, and the other is measurement, well, I don't know, the other person's measurement goes that way. 2, that one has got a measurement that way and a measurement that way, and 3, oops, it's a measurement, another measurement that way and a measurement that way. 4, measurement that way, and 4, a measurement that way, and 5, a measurement that way again, and that way, and 6, a measurement that way again, and a measurement that way, and 7 is a measurement that way, and 7 here is a measurement that way, another measurement that way, and a measurement that way, and another measurement that way, and a measurement that way. So these are the 9 possibilities. Now, according to Gulick-Stern, they can either go, spins can either go that way or that way. They never go anywhere in between. So I've actually got a magnetic field here like this. So we want the probability that these particles will fall to the right. Okay, so now they should 100% of the time they're going to fall in opposite directions. Okay, so according to the hidden variable thing, if they're actually in this top state here 1, they both would fall the same way, and the probability of that is 0, because they're going to 100% probability that they're going to fall the opposite way. What about the second scenario? They're falling an opposite way. That's 100% likely. Third scenario, they're falling the same way, no probability at all. 4 opposite ways, they're going to fall 100% probability. 5 falling the same way, that's not going to happen. 6 falling opposite ways, that'll happen 100%. 7 falling opposite ways, that's 100% probability. 8 falling the same way, 0 probability. 9 falling opposite ways, that's 100% probability. So here we add up how many times you get a successful result. 1, 2, 3, 4, 5. Okay, the answer is 5 out of 9. Now that's called an inequality, because it's not 50%. They're not equal probabilities of falling the same way, of falling opposite ways. So that's called an inequality. Now, what does quantum mechanics say? Well, it's a bit more subtle, because let me just make that bigger. It says that, okay, we want to know the probability of it falling to the right, okay? So it says, well, these particles are actually in these quantum states, and the probability requires a bit of algebra. And so what you do is you get the angle here, and then you go cosine of that angle. In this case, it happens to be 60 degrees. You halve it, spin half particle, and you square it, and the answer you get is a 75% probability for that one. And what is that length? Well, it's actually, let me do another colour. It's actually that, it's just that length there. It's 0.75 of 1. Okay, if 1 being the total diameter of that circle. So that's all how it's worked out. Okay, so let's look at the probabilities. Okay, so just looking at this one alone, the probability of it falling to the right is the cosine of, and now in this case our angle is 180 degrees, so it's 180 degrees divided by 2 squared, and that probability is 0. Okay, so without doing any more calculations, the probability of that one's 0, that one's 0, that one's 0. What about this one here? Well, I said it's 75%. What about that? And they're all 75% because from there to there, they're all 75%. They're all 0. What about these ones? They're also 75% probabilities. And what you do is you just add them all up. So you've got 6 75s plus 3 zeros, and then there's 9 possibilities. It comes to exactly 50% overall. Let's look at these ones. Again, you do the same thing, and it turns out that the probability of that one falling to the right is 25%, probability of that one falling to the right is 25%, probability of that one falling to the right is 100%. Okay, so you've just got 25% probability, 100% probability, 25% probability, another 25%, 100%, 25%, 25%, 100%, 25%. You just add all those up and you get a total of 450% out of 500% because you've got 9 possibilities. Divided by 9 possibilities, you get 50% again, exactly. So this inequality down here is violated. So Bell's inequality is violated. In other words, there is a quantum reality which is subtle, which has got this probability. In other words, there is a reality called a quantum reality as well as a classical reality. That's what I take out of it anyway. Yeah, that'll do for that one.